So we'll be able to move, is this one? We'll be able to move to light waves. All right, let's begin now. Let's begin. Are we ready? So now we talked about the characteristics of waves, right? Before we fully delve into the characteristics, I've explained them briefly, right? Now you must remember them. You must remember them. Um, we talked about reflection, right? Refraction, diffraction, and what? Interference, polarization. Right. Now watch. Reflection. These three are change in direction. I talked about that, right? So this one is change in direction when the wave strikes an obstacle and then bounces off the obstacle. That's reflection. So for sound, for example, it is what leads to echo, right? Good. For stationary waves, if you tie a string, if you tie a string on two poles, you pass a wave here, it returns in the opposite direction, right? Two equal waves traveling in opposite direction. Do you understand now? So that is reflection, they bounce off and return. Then refraction, this is what that. Now these two have to do with light, but this one is what reflection is what happens with mirrors. So when light touches mirror, it gets reflected back. That's why you're able to see yourself through the mirror. Is it making sense? Refraction happens with lenses like this. Even though this one is not lens, it's not like your lens. Do you understand? We talk about your lens, exactly. So lenses, refraction is what happens in lens. That is, light will enter into a material and come out on the other side, but in a different direction. So it's called refraction. It's called the bending of light because it's traveling from a medium of low optical density to a medium of high optical density, or medium of low high optical density to a medium of low optical density. I'll explain what that means. That's when we get to it in detail. Then diffraction is when it is traveling through an aperture. When light is traveling through a small aperture, so then you've seen this thing before. If you illuminate a small hole, you notice that the light will travel like this, right? And go and form something big. Eh? Oh, okay, yes. So the thing, what I'm trying to say is that that spreading there is the diffraction, okay? It's bending around obstacles. Exactly. So it's bending around obstacles. That's one of the principles. That's the principle that by which this guy operates. A pinhole camera. Pinhole camera operates on the principle of what? Diffraction. Yeah, there's a small hole through which you illuminate. For example, I'll show you under reflection, don't worry. Then interference. Interference simply means two ways. They are interfere means they are here. We call it superimposition or superposition. Superimposition or superposition. The principle of superposition is based on two things. One, the waves must travel, they must have coherent source, and they must coherent source simply means their source of vibration is the same, okay, and they are polarized along the same side. There are two types of interference. I want to use it to explain. There's one that is called constructive interference, the other is called destructive interference. If I pass wave on one side of the rope, and that loop goes like this, and I pass another wave on the other side of the rope. Now these two, they are coherent. Why? They have coherent sources because they're happening on the same rope. Exactly. Now if these two waves, when they come together, if they are both making troughs, since they are both troughs and crests, rather, this is crest, right? If they are both crests, when they meet here, for example, they will create a larger crest. This is called constructive interference. It's called what? But if I pass wave here, if I pass a crest here, and now pass a trough here. When they meet, they will cancel out each other. It's called destructive interference. Is that right? Do you understand constructive and destructive now? So if there's a crest, a big crest, and a small crest, when they meet, they will still give a larger crest. That is constructive. They construct something. Think of it that way. Then if a crest that is meeting a trough, it will cancel out. But it will become zero only if the magnitude of the amplitude for the crest is the same as the trough. But if this one is maybe small like this, and this one is this big, now what will happen is that it will only reduce the crest. Is it making sense? But it's still destructive. Do you understand? Alright. The polarization is this. Now, we talked about electromagnetic waves. We described it into two. We said longitudinal and transverse. We said electromagnetic waves are transverse because they travel, and it is when electric field and magnetic field are perpendicular to each other, right? So now, for example, this white light that we see, we said is polychromatic because it contains Roig right? Roig red, orange. So white light is polychromatic. Okay? But your light from laser is usually which color? Red, right? So that's monochromatic. That's what? Chromo. The word chrome. Google Chrome. What do you see? Different colors, right? The word chromo means color. Exactly. You hear chromosome in biology too. Colored bodies. Soma means body. So chromosome. Colored bodies. Is it correct? So plenty color. Make sense? Mono, single color. Alright, so I now say that these are white lights, for example. You cannot, to polarize it, you put something called a polaroid. We said there are two waves traveling for white lights. There are two waves. The electric wave like this, then the magnetic wave in and out of the board. Do you understand this diagram? One is traveling up and down the plane, one is into the board, one is out of the board, into the board, out of the board. Is it clear to us? Just manage the diagram for now. Is it clear to you? This wave is traveling into and out of the board like this. This one here is going up. Let's call this the electric field. So this one is going up and down on the plane here. Then the other one, so one is going like this. The other one is going like this. Is it making sense now? So let's call that one maybe B field, for example. It's not so apparent, that's why it's not clear. Oh, okay, sorry. That's like this. So this will be like let's call this the E field, this will be the B field. This is magnetic field, this is electric field. That's right. So what will you do? What's the polaroid? You now put something like this. This is a polaroid, you see now. Now looking at this thing, which wave will pass through this aperture here? Which wave? Is it the electric field or the magnetic field? That will pass through that thing. It's the electric field. It's the electric field. And you should trace it. I intentionally asked the question because I wanted you to trace it. My diagram is not perfect, that's why. See, electric field is the one going like this. The magnetic field is the one going like this. Into the board and out of the board. And I'll put something like that. And I'll say which one will pass through. Is it this one or this one? This wave here is combination of these two. Yes. Alright. So which one will pass through? The first one, right? So what will happen? This thing is called a polaroid. This is called what? Polaroid. Alright. The common polaroid that they ask about is tourmaline. Now actually, let me tell you the use of polarization. This polarization causing a transverse wave to causing a wave that is transverse, okay, to be absorbed. That one of the spectrum be absorbed, the other be allowed to pass through. Meaning that if I want this thing, if this electric field If I want the magnetic field to pass through, how do I position my Polaroid? Like this, right? So if I place it like this one will pass through, then this one will be absorbed. So this thing contains materials that can absorb the other wave that is not in this orientation. So since this guy is in this orientation, it will allow this guy to pass through, but every other wave we enter will be absorbed in all this side. Is it clear? So that's what polarization does. Allows one wave to pass through and absorb the other part of the wave. Is it clear? All right. So now, I now said that interference having to do with this thing. Now, transverse waves cannot be polarized, cannot interfere except they are polarized. Do you understand what I just said? You know that this wave, for polarization to occur, one wave has to be traveling the same, they have to be coherent in source. So if they are coherent in source, it means that it can only, we need to cause interference now, we need another wave that has to be vibrating at the E field and the B field axis too. Do you understand? And in fact, in that case, it means interference will occur in this axis and in this axis. Do you understand? So that's why it's hard to cause interference of electromagnetic waves or transverse waves altogether. Do you understand? It's only when you polarize them. For example, if I polarize this wave now, if it were like this, like we said, just manage it there. If we polarize it such that this wave, which wave are we going to see at the back? This, right? So to cause this one to interfere, it will be interfering with another polarized wave. Do you understand? Such that the part that is also polarized, that is allowing to pass, is also the E field, as in this case. I don't know if you understand. Do we understand? I know what's confusing you. You do you understand though? I should explain. Watch. If for an electromagnetic wave, we have that it is formed when B field and E field they are interfering. Let's call this one the E field, for example. Then the B field will be like this. You know this one is up and down, right? The other one is into the board and out of the board. Now, I cannot, this wave is hard to interfere. Interference, it will be hard for this one to undergo interference, to be superimposed, because I need another wave. You know, I said the condition for interference is that they must have coherent sources, right? It means that they must have the same frequency of vibration, the same the amplitude may not be the same, but they must come from the same source. They must have the same angular speed, all those things. You understand? It's just the amplitude that might differ, right? So if I must polarize it, if interference must happen with this guy, then I need another wave that is having both electric field and magnetic field that are in this orientation. Do you understand? So it's hard to cause interference here. For me to cause interference, I need to polarize it. Polarize it means make one wave to pass through. So for example, I use a Polaroid in this orientation. Which wave will make it through? E field or B field? E field, right? So the E field makes it out like this. So is this one now that I can now cause to interfere with another one that has been polarized too with the same orientation? Do you understand now? If I have another wave from the other side, for example, well, it may not be from the other side, it may be just beside it, that's going in the same direction. That's why this is what I'm saying on the other side, because coherent source means they must be on the same line, they must travel on the same line, they must meet each other. That's not interfere. They touch each other. If they are traveling in different directions, if they are in different phase sides, they will not touch each other. Exactly. They must have the same phase too. Do you understand? That is, if wave one has is if the face the way the rate at which the face is changing must be the rate at which the face of that one too is changing. I mean, if not, they cannot have the same frequency. You understand that one, right? Like they say. What I'm saying is, a wave like there's like this cannot interfere with a wave like there's this. Right? Which one has higher frequency? Wave from A or wave from B? Wave from B has higher frequency. Higher frequency. This one has higher frequency than this. Do you understand that? So I cannot cause this to interfere. This one can only interfere with another waveform that's coming on the other side that has similar. You see that they are progressing the same way. Do you understand? All right. This is the B field, into and out of the board. This is the B field. This is the magnetic field. No, okay, for this one, this is the magnetic field. This one is magnetic field. This is the E field. She's correct when she said E field. Is E field that will pass through? E field will pass through here.
I thought when you did,
I changed it, yes, I changed it. I didn't change it there. Before I put this one as E field, right? And put this one as B field. It shouldn't confuse you, whichever way I put it.
Okay, anyone can be.
As far as they are traveling at 90 degrees to each other. Do you understand now? Right. So you get the condition for interference. And I've used it to explain polarization too. They must be traveling at the same with the same phase, at the same frequency, coherent sources. Do you understand now? All right. Now let's quickly. I'm trying to rush because that's not where we are going to. Now let's start with what we want to do now. So Marlene is a type of polaroid. Remember. One of the use of polarization is this sunglasses. I used to have one. Yeah, I will probably bring it next time. Sunshade. You know when there's eclipse, we talk about eclipse too. You know they will tell you to put on one black glass like this, one shade. To look at, you've never observed an eclipse before.
When solar eclipse happen now.
Okay. Whenever there is eclipse, it's okay. You know why people wear shades sometimes? It's because of the sun now. Do you know what it does?
It's a block now.
Yes. What it's doing is polarizing. It's polarizing the light. Do you understand? So that's the function, that's the practical use of polarization. Exactly. Sunglasses. Right. Now let's go to wave equation. We'll now deal with reflection. We'll now begin with reflection. We'll have to know the wave equation because we won't go back to it once we start reflection. Now the wave equation. Remember though that I told you wave is defined tempospatially. But a waveform is defined by this equation. This waveform, for example, we talk about the vertical displacement. And since it's a circle, we use cyclical motion. You can use motion in a circle to organize it. You will understand now. You know this is a circle, right? This is a complete circle, right? If a particle is that, keep in mind I told you that simple harmonic motion is different from wave motion because simple harmonic motion is one particle oscillator, but wave motion, many particles oscillator. So if a particular particle is here, you want to know the vertical displacement from this position, from the equilibrium position. If it's here, it is one point in the circle, right? It's at one point. If it's here, it is at one point in the circle. So we want to know its distance from the horizontal position. This is it. If this is a circle, we moved, for example, if we start from here, we moved like this and like this. Make sense? So a wave particle that is here could be somewhere here. So we want to know its displacement from the starting point. Do you understand? It's just like vector analysis. Do you understand now? Using the positions that we normally use, y component and x component. Good now. So to know the y component of this thing, at this point, what do we do now? This is what we'll do. You know that from here to here, every point here is the radius, right? which corresponds to the amplitude of this guy. So I will say from here to here is the amplitude of this guy. And this guy, our particle is at this point. We use any point to show you that it's the same. What we want to do is find the horizon, the vertical position, vertical displacement away from this equilibrium position. Is it clear? Don't worry, I will use another point. So this is the y that we're looking for. Let me use another point. Let's say our particle went and got here. Let's call this one particle X, no, particle J. Let's use M, particle M. This one particle N has gotten here. What you will understand, this analysis, I want to understand why we analyze this way, how we're analyzing it. I don't want to just bring the equation that you not know where it's coming from. So now, here, welcome. Now we got here. This our particle has gotten here. We want to know how far away from this equilibrium position it is, right? So we know that it has an amplitude A, right? And it's going to be a distance y. Is it making sense?
Yes.
If it's here, if it's at this position, let's call this one particle O, for example. It has amplitude A, which will be the same throughout because it's the same radius. The horizontal position from starting point to what? Vertical position from vertical displacement from starting point. Yeah, we can. I'm trying to show you that any way that we are analyzing is good. We can use this analysis to get it. This thing I'm showing you to get it. Is on this side we use this. On this side we use this. Even though this one with different y positions, you know, y2, y3. Is it making sense? Yeah. But let's use y1 for example now. For y1, it is at an angle from the starting point, right? Now, what relative to this triangle, what sides do we have? We have y and a. What is this side? What is this side? So which function combines sine, right? So the sine of theta is equal to opposite, which is what? Negative. So our y will be equal to what? A sine theta. Does this make sense? We soon get there. Just come now. You will notice that we use even this particle, to explain it. This y2, for example, it will be at an angle away from that same position. So what side do we still have? Opposite and hypotenuse. Makes sense? So it was sine theta equal to y over a, y2 over a, right? So y2 is equal to what? A sine theta. This is the same wherever we analyze from. Do you now understand? Good. Is it making sense? Good. Now watch. So we understand therefore that the vertical displacement from equilibrium position of our wave is always amplitude sine theta. Is it making sense? But wait, you know that if it were simple harmonic motion, it would be one particle that is oscillating back and forth. But wave, I said there are many particles, right? So any particle we are looking at is always at some distance away from another reference particle. I don't know if you understand. This wave is not one particle that is oscillating. Many particles. So if we want to describe the position of one particle, we cannot describe it without referencing it with another particle. Do you understand? So we'll say that two particles will be at a phase difference from each other. That's what we're doing in phase A and between A and B, point B and D, point E and F. Do you understand now? So those distances. So from here, for example, I want to describe this particle. If I put a particle A here, and I put a particle B, a particle C, I want to describe particle A. If I want to describe it, I need to describe it with respect to either particle B or particle C. And if I will describe it with respect to particle B, they are at a phase difference. Do you understand now? They are at a phase difference. Relative to the beginning, we have used a sine theta to get it. But if I must describe it, I must describe it with respect to any other particle on this side. And they are at a phase difference from each other. So I have to subtract that is different. Is it clear? All right. So we'll put this in bracket. So from here we can begin to derive our equations. We know therefore that y equal to, remember how we did in cycle in the beginning of that this thing, that theta is equal to what's formula for speed, for velocity? Displacement over time. Good. So if I am talking about angular speed, therefore, then it will be from here to here, for example, is an angle theta, right? So it will be angular displacement, the angle that I displace per unit of time. Do you understand? You know velocity normally is displacement over time. It is now angular velocity. It will be